Hello, you absolute legends. My name is Eric J. Choi, and I'll be explainer video 4.1, which talks about light passing through a liquid and having to find the wavelength of the light as it passes through that liquid. Jumping right into the problem. A helium neon laser beam has a wavelength in air of 633 nanometers, and it takes 1.38 nanoseconds for the light to travel through 30 centimeters of an unknown liquid. What is the wavelength of the laser beam inside that liquid? Now, as you can see right here, I drew a diagram of the problem, and I don't know what a helium neon laser beam looks like, so here's a lightsaber shining its light through a faucet leaking an unknown liquid that is approximately 30 centimeters in width. Now, we know that the wavelength out here is different from the wavelength that's inside the liquid, and so that's actually, once the light enters the liquid, it actually slows down the light and causes it to take longer to come out than before. So we're trying to find the wavelength in this liquid as explained right here. Now, what did the problem actually give us to start off the problem? So far we know the wavelength in the air is 633 nanometers, which when converted to meters is 633 times 10 to the negative 9 meters. We all know the velocity of light, or the speed of light, to be 3 times 10 to the 8th meters per second. And we know the distance, or rather the width of the liquid coming out from the faucet, is 30 centimeters, or 0.3 meters. And we also know that the time it takes for light to go through that liquid, right here, is 1.38 nanoseconds, or rather 1.38 times 10 to the 9 seconds. Now that we have all our given toolbox values converted and ready to use, we can now start the problem. Now, we all know that velocity is equal to distance over time. It's a basic formula. So using our pieces from up here, 0.3 meters over 1.38 times 10 to the negative 9 seconds, we find that the velocity inside the liquid is 2.17 times 10 to the 8th meters per second. Now that we know this key information, we are allowed to use this formula right here. Velocity is equal to the wavelength times the frequency. Now, if we try to change this formula to account for the liquid, we end up with the velocity of the liquid is equal to the wavelength of the liquid, which is what we're looking for, times an unknown frequency. But is it really unknown? Here's some review for you guys. When light goes from a vacuum, or in this case the air, to any medium, the velocity in the lambda might change, but the frequency will always stay the same. So that means even though there's two unknowns in this equation right here, we can actually find the frequency using the frequency from the speed of light equation. So using the same exact formula above, v is equal to lambda f, except changing it for the speed of light, we end up with c is equal to f times lambda of the air. And if we rearrange this to isolate out f, we get f is equal to the speed of light divided by the wavelength of the air. Now that we have one of our unknowns solved, we can actually plug it into the above equation right here. So we ultimately end up with the velocity of the liquid is equal to speed of light over lambda of the air times lambda of the liquid. Since we're trying to find the lambda of the liquid, we isolate it out to the other side and step by step plug and chug all the values into our equation until we finally end up with a final answer of 450, oh, there's a typo right there, 458 nanometers. Let me fix that real quick. There we go. It's good to double check these stuff. I hope you guys understood all that, and I hope you guys have a nice day. You absolute legends.